Okay, thank you for the introduction and for the invitation to speak at this conference. Okay, so I will not assume that anybody knows anything about free cumulants, so I will say a few words. So I will start with cumulants, which I think are familiar. So if we have random variables and we take the logarithm of the Laplace transform, we can expand this into a series. And the coefficients are the cumulants of the random variables. They are just polynomial in the moments of the joint moments of the random variables. And for example, the first cumulant is just the expectation, the second is the covariance, and so on. So we have an explicit formula. Now there is a combinatorial formula in order to compute these objects. For this, I use a set of set partitions of numbers from 1 to n. And there is a way to write the moment, the expectation of the product, x1, xn, into a sum of products of classical cumulants, the k's. So here, pi is a partition of 1n, and k pi is a product over all the parts of the partition of k evaluated on the elements, on the x indexed by its elements of the part. Okay. So in order to make this concrete, this is the formula that you get for the first few n's. So we get the expectation, which is the first cumulant, the expectation of the product, and so on. And the formula that I showed before is just the inversion of this formula. I mean, going from moments to cumulants is a triangular system that you can solve easily by induction. Okay. So what are cumulants useful for? Well, for one thing, they encode independence of random variables. Now, suppose you have your random variables that generate an algebra, A, of random variables, and suppose you have some subalgebras of random variables which are measurable with respect to some sigma fields. Then you can test the independence of the subalgebras by looking at the cumulants, and independence is equivalent to the fact that the mixed cumulants vanish. Okay, so you look at kn of x1, xn. So xij belongs to one of the algebras, not aj, just one of the algebras. And as soon as two of them belong to two different algebras, the cumulant vanish. Okay, so that you can test easily. You can test easily if the random variables are or the algebras are independent by looking at cumulants. Another reason why they are interesting is that they allow to analyze fluctuations of random variables. Okay, if you know about large deviation theory, I mean, as you see, they are just the logarithm of they intervene in the logarithm of the Laplace transform, so clearly they are related to large deviation functions. Okay, now I will come to free cumulants, which are probably less familiar to most. What are free cumulants? Free cumulants are built in a similar way, but instead of looking at the set of all partitions of the set 1n, I will look at a subset which are called the non-crossing partitions. So what is a crossing in a partition? It's 4 elements, a, j, k, l. So these are set partitions. And I assume that a and k belong to the same part, j and l belong to the same part, but they belong to two different parts. Okay. So a partition is non-crossing if this configuration doesn't exist in the partition. Okay. So typically, one draws the partitions, non-crossing partitions, in this way. So you put them on a circle, like this, at the roots of unity. And then, I take a typical partition of 1n, and for each part of the partition, I draw the polygon whose vertices are given by the numbers in the part of the partition. And the partition is non-crossing exactly when these polygons are disjoint. I mean, they do not cross. Okay. So, for example, if I choose to put 2 in the same part of 6 and 8 in this diagram, then I would produce crossings, and my partition would not be a non-crossing partition. Okay, so I mean these objects are very popular in combinatorics. They are counted by catalog numbers, like many examples of combinatorial objects. So they have been of use to define the free cumulants that I'm going to define. And the formula for the free cumulants is very similar to the formula for the cumulants that I showed before. It's a combinatorial formula. But the context is different. It's not for usual random variables, but rather for generalization, I mean, non-commutative random variable, which we find, I mean, basically operators that you may find when you do quantum mechanics. Okay, so suppose you have a K-algebra, which contains a unit, and a linear form, phi, from A to some field. I mean, here we will talk just about complex numbers, which is 1 on the unit. A typical example is just the algebra of matrices of complex numbers, and phi is a trace, normalized trace, so that the trace of the identity is 1. And we should think of the elements of A as non-commutative random variables, and phi, we should think of it as the expectation. Okay. Now the free cumulants, they are defined in an implicit way, exactly by the similar formula that we had in the case of cumulants. So I look at a phi of a product of elements, A1, A2, AN, and this is equal to the sum of all non-crossing partitions of R pi. So R pi is defined in terms of, I mean, I will show you the formula. It will be easier to understand with the formulas for small n. R pi evaluated on A1, AN. Here R pi is a product of all the parts of the partitions of the R evaluated on the elements in the part of the partition. So maybe some examples. So the first case is just the expectation. So phi of A1 is just R1 of A1. So the R are indexed by each Rn is an n-linear form on the algebra. And so the second formula tells you that you have 2 partitions, and there are two of them are non-crossing of 1, 2. So you have 2 terms in the sum that I showed you. And now you can solve the system because you already know what is R1, so you can deduce the value of R2, which is given, so I should use this way. Does it work? Yes. Okay, so you get the value of R2 from this. So for when you look at partitions of 3 elements, so you have more terms. There are 5 partitions, and for each of them, you write. So I wrote the partition on the right, and the terms R pi corresponding on the left. Okay, so for example, for these partitions, which is 1 and 2, 3, I got a term R1 of A1 and R2 of A2, A3. Okay, I write this formula, and now in this formula I already know what are R1 and R2, so I can deduce easily R3. And so in this way I get a triangular system that I can solve explicitly. And actually I show you the formula for R3. Incidentally, since there are no crossing partition for n smaller than 3, the formulas are the same in this case for the cumulants K and the non-crossing cumulants. But as soon as n is larger than 4, the formulas are different. And another thing is that in these formulas, the order of the product in the product is important. You cannot change because you do not assume that the algebra is commutative. So the order in which you take the product, for example, A1, A2, A3 here, is important. So in particular, even if the R commute is a A commute, the R is not symmetric. It's not a symmetric function of the A. That's an important remark. Okay, so now let me give an example. Which will be used in the sequel. So take an element A in A and look at its moments. The moments are just phi evaluated on the monomials in A, phi of AN, like the moments of a random variable. and look at its ordinary generating series. So I'm looking at the ordinary generating series. When I was looking at cumulants, I was looking at the exponential generating series, which is the Laplace transform. Okay, so I'm looking at this ordinary generating series. Now, if you make the generating series obtained by looking at the numbers Rn evaluated at n times, okay, these two series, M and R, are related by this equation. I mean, essentially, R is obtained by inverting M, up to some twists, but essentially this is the idea. Okay, so we have an equation which is before in the classical case. I mean, in the case of classical cumulants, we had the logarithm of the Laplace transform, but here we have this function R, which is obtained by inverting some power series. Okay, so in particular, we can express the Rn of AAA in terms of the moments by some polynomial formulas, and we already knew that. So, what I use these free cumulants useful for? Well, now we can make a definition of something which is called a free independence using these non-crossing cumulants in the following way. I mean, it is exactly the similar formula as similar definition as what we had in the case of the cumulants. We have an algebra A with our linear form phi, and we look at subalgebras AI, and we will say that they are free, meaning freely independent, which is not the same as independent. If and only if all the mixed cumulants vanish. So a mixed cumulant is exactly as we had before, Rn evaluated on a family A1, An, where each AI belongs to one of the algebras, and a mixed cumulant means that at least two of the algebras appear in this sequence. Okay, so there exists at least two of these elements which belong to two different algebras. If this occurs, then this is zero, and this is a definition for the freeness of the subalgebras. Okay, so this is a notion of independence which is suitable for non-commutative random variables, and typical examples are random matrices. Actually, the original definition of freeness was not this one. It was another definition which was provided by Voiculescu around 1983. But then Speicher around 1990 developed the theory of free cumulants and showed that the original definition of Voiculescu is equivalent to the one that I showed you before. Okay. So this has many applications in mathematics, in operator algebras, and also in random matrices. And the reason for that is that if you look at large independent random matrices, I mean for many models of large independent random matrices, when the dimension goes to infinity, they behave like if they were free random variables in some sense. Okay, so for this reason, so there's been a lot of applications of free probability to random matrix theory, in particular to understanding the spectra of random matrices and things like that. Okay, so let me show you a connection between free cumulants and matrix integral. Maybe the simplest way to see free cumulants appearing in matrix integrals. For this, I take the following model. I take a lambda, a diagonal matrix with eigenvalues lambda 1, lambda n, say Hermitian. Okay, and M will be a random matrix obtained by conjugating conjugating lambda by U, a unitary, which I choose with a Haar measure, with dimension big N. Okay, and I will assume that N goes to infinity, and that the empirical measure on the eigenvalues converges to some probability distribution mu. Okay, so you imagine you have your large random matrix. It is a typical random matrix with spectrum. The spectrum is fixed, if you want, and the eigenvectors are chosen at random, in the most random possible way, that is with a Haar measure. And now, we look at the upper left corner of the matrix, M11, and we look at its Q's cumulant. That is the cumulant of M11 repeated Q times. Okay. If I rescale this cumulant when n goes to infinity by n to the Q minus 1, this will converge to the free cumulants of mu, the Q's cumulant of mu with a factor Q minus 1. And here, RQ of mu is just RQ of x evaluated repeated Q times. So x here is some random variable with u, low mu. Okay. And okay, so this has been proved several times with several refinement on the hypothesis and the conclusions, more or less strong conclusion. And of course, everything depends on how fast the measure, the empirical measure converges to mu. So you have several ways of understanding, stating this theorem. Okay, so now since free cumulants have appeared, we have seen them occur also in other fields, and I will cite two examples in which I played a role. So the first is the evaluation of characters of large symmetric groups. It turns out that if you look at very large symmetric groups and characters of their representations, and you have to satisfy some hypothesis on the size of the Young diagrams corresponding to the representation, then asymptotically the value of the characters evaluated on a product of a few cycles of the in the symmetric group can be expressed in terms of free cumulants of a certain measure which is associated to the Young diagram. Another field where free cumulants have appeared a bit quite unexpectedly is the enumeration of braids, and that was actually I was contacted about 10 years ago by Patrick de Hornoy, who had a sequence which appeared in enumeration of braids related to gas size structure. I will not give any more details, but quite accidentally I discovered that these were actually free cumulants of some probability measure. That was completely unexpected, but okay. But I will not give any more detail about that. But there are many more examples of free cumulants appear in nature, and now, but I mean, the free cumulants which appear here are free cumulants of probability measures, that is one-dimensional free cumulants. But now what I want to do is to show you how free cumulants appear are related to the fluctuations of in the exclusion process. Okay, so this is a recent work, so I will explain this. So first, a review of the classical exclusion process. So the classical exclusion process is, to describe it, it's you have an interval, discrete interval with n spots, and at each side of the interval you can have either a particle or no particle at all. Each particle may decide to jump to the left or to the right with some probability, p or 1 minus p. Well, in the following, I will just consider the symmetric case, p equal 1/2. But also there is some provision that if a particle wants to jump to a site that is already occupied, then it doesn't jump. Okay, it remains where it is. But on the other hand, if it wants to jump to an empty site, there's no problem; it will jump. There are also particles which come in and come out of the interval from the left or from the right at some rate, alpha, beta, gamma, delta. Okay. So this is a very well-known model, very much studied. There are lots of papers about this model, and a lot is known. So one of the interesting things is the stationary measure. Okay, so what we see is that this process defines a Markov chain on the set of configuration The configuration is just tells you just where are the occupied side and the empty sides. So it's just if you want 0, 1 to the n. So 0 is just empty and the 1 is occupied side. So in the large time limit, there is so we see that the configuration of particles converges to a stationary measure mu on omega. So because it is open at the left and at the right as the interval, so particle may enter or exit. This is this system is out of equilibrium, so it's different from many others statistical. Well, it's a most typical, one of the most typical example of statistical system out of equilibrium. So depending on the values of the rates at the boundaries, so a certain a certain current will be established when particles will have a tendency to move either to the left or to the right. Okay. Okay. So one of the interesting objects is a density profile. Okay. So we will look at this object, the stationary measure, and what happens when n goes to infinity. Well, when n goes to infinity, it's possible to define a density profile. So when n goes to infinity and we rescale the interval so that it fits into the interval 0, 1, the real interval 0, 1, then the number of particles, which is in a very small interval near x, so here it's xn, x plus delta xn, if I look at the integer parameters, the integer coordinates. So the number of particles will converge. So this density profile, telling you the local density, it will converge to a linear function on 0, 1. Of course, the parameters, so this linear function as of the form n of x is n0 plus n1 minus n0x. That should be, the t here should be an x, of course. And of course, the linear function depends on the inputs, that is on the rate that you get on the left or on the right for the particles to enter or to exit the interval. Okay. A famous result is a result by Derrida, Lebowitz, and Speer, which tell you what are the large deviations for the density profile. So here I showed you, I'm not sure everybody can see, there is a little red curve. I'm not sure, can you see the red curve? Or, okay. So there is a little variation of you have the density profile, the limit density profile, which is a straight line. And you look at a small variation of this density profile, which I call x. And now the probability that density profile is close to some function, h, as n goes to infinity, will behave with decrease exponentially, e to the n minus I of h, where I is a large deviation functional. Okay, so this is a typical large deviation result. And this large deviation functional was computed by Derrida, Lebowitz, and Speer. 2001. So here is the formula, which may not be too easy to understand, but okay, that you have to maximize a certain functional of h, where you have introduced a function f, which is monotone, with f0 is equal. Well, I'm not sure. It's maybe f of 0 should be equal to h of 0 and f of 1. I'm not exactly sure about the boundary condition, but anyway, you have an explicit formula for this function. For this, you have to maximize a certain functional, and the important fact is that if you change h, you make a local change of h, the function h, the function f will have a global change. I mean, it's a non-local formula in this sense, and this is a way of saying that this process has large range correlations. I mean, the stationary measure has large range correlations, and this formula has been established using the matrix ansatz, which is a method for solving the symmetric exclusion process. Okay, so it's a kind of trick which works very well and allows to produce a lot of results. I mean, in some sense, this model is solvable. Okay, so what I will show you is that actually there are some free cumulants which are hidden behind this formula for the large deviation function. And for this, I will use another process, which is a quantum version of the symmetric exclusion process. Okay, so this quantum version was introduced a few years ago, and I was introduced to this by Denis Bernard, who asked me a question a few years ago that fortunately I was able to answer, and then we started working on this with Michel Bauer, Denis Bernard, and Ludwig Roussat. Okay. So what is a quantum symmetric simple exclusion process? Okay, so it's a quantum process. So this means that we have fermionic particles, and there is a Hamiltonian. So what is the Hamiltonian? The Hamiltonian can be written as a sum of, so there are several terms in this sum. There are first a Brownian motion, or more precisely several Brownian motions, independent complex Brownian motions. They provide the noise that will drive the particles. And the Cj here, they are fermionic creation and annihilation operators, and they satisfy canonical anti-commutation relations. So these are, well, they satisfy other relations like the Ci should anti-commute, Ci dagger should anti-commute, but okay, so this is so it is a very classical set of fermionic operators. And they act on this space, V, which is C2 to the tensor n, okay? And so we have, what we have, HT is random because you have a Brownian motion, so you have some randomness. It's random, but it's a random operator, so if you want, this is a random matrix, okay? A random matrix acting on the space V. Okay, so what is the correspondence between the classical and the quantum? So there is a reason why one should call this quantum version of the exclusion process, is that so V as a linear space is a quantum version of omega, which is the state space that we had before. So just V is just a linear span of it's just a set of, if you want, wave functions on omega. If you have a state which is a product state, so each C2 has a basis which consists of E0 and E1. E0 corresponds to an empty site, E1 to an occupied site, and a state of this form, a product state, corresponds to classical configuration in some sense. Okay, so HT is a self-adjoint operator which evolves randomly. Okay, and now what happens? Now if you want to look at the particle at some time t, okay, you will perform an experiment, a quantum experiment, and this quantum experiment will be described by a density matrix. This density matrix, rho t, it is a positive Hermitian operator on the space V, whose trace is equal to 1, so it's the quantum analog of a probability measure. And it will satisfy, the rho t will satisfy a differential equation, okay? So the first part of the differential equation, this is the usual equation that you get when you look at a Hamiltonian, depending on the time. Okay, so the derivative of rho t is the commutator of rho t with h. But there is another term here, which is where you see a double dh. This comes from the Ito formula because remember that h is a Brownian motion essentially, a matrix valued Brownian motion. So when we can write products of dh, and it's non-zero because we have the quadratic variation of the Brownian motion. And finally, there is another term which is here, which I called L boundary. This is a boundary term. These boundary terms tell you what happens at the boundaries on the left and on the right. I don't write it here, but I mean, there is a formula for implementing that. It tells you that some particles may enter or exit on the left or on the right. Okay, but you have to supply this, but it is essentially a linear term. So oops. Okay. Now ρT is a random matrix. Okay, I said it is a positive definite matrix evolving with time. Now, if the initial configuration of the particles is diagonal, that is, it's a classical state, then it will be the expected value of ρT will also it will be also classical, and it will satisfy the same evolution as the classical exclusion process. So this is why this is really a quantum. It's a quantum version, but also it projects onto the classical exclusion process. Okay, so in particular, what we can deduce from that is that if we look at the occupation number of the classical exclusion process, I will call them tau I. Tau I is a random variable on your process, which is 0 if the site I is empty, and 1 if the site I is occupied. Okay, so these are the random variables under the stationary measure of the classical exclusion process. So you may want to compute their John distribution, and this actually can be expressed in terms of the quantum version. So the formula is just the following: the expectation, so the Laplace transform of this tau j, they correspond to the Laplace transform of the quantum operators, the Ci dagger Ci. The Ci dagger Ci are operators which count if there is a particle at site I. I mean, they are the quantum version of the tau I in the quantum model of the QSSEP. So what you have to do is you have to take so on the left you have the classical random variable, and on the right you have the quantum. So you have so rho infinity is the limiting value of ρT. So when tau goes to infinity, it converges to a random emission matrix, random positive definite matrix, random density matrix, and this tells you that actually you can represent the classical exclusion process in terms of the quantum. So the quantum is some sense above the classical. It projects onto the classical process.
So, and the expectation is on the Brownian motion?
Yes. Okay. Of course, it is. In the end, what you get is rho infinity is a random. Well, it's in the Brownian. It's not really in the Brownian motion. It's a convergent in law. So you have some rho infinity is a random matrix, random density matrix. So the expectation is with respect to this randomness. Okay. The Brownian motion, you use it to generate the thing, but of course, in the limit, you have a stationary distribution, and there is no Brownian motion. Okay. Now rho is a matrix of size 2 to the n. Okay. But there is some feature of the Hamiltonian, which is it is quadratic. This Hamiltonian is quadratic in the creation annihilation operators, and because of that, actually the matrix rho is the fermionic analog of a Gaussian matrix. In particular, it is completely determined by its correlation function. Okay, exactly like a Gaussian random variable, a Gaussian vector is determined by its correlation, its covariance. So it's the same for the matrix rho. So we can reduce all the information which is in rho into the information of the correlation matrix. And you can go from one to the other by essentially Wick's formula. So Gij is just the correlation of the creation operator at site j and the annihilation operator at site I. Okay. Now these random variables, Gij, so they form a Hermitian matrix, and so they encode the correlations between the site I and the site j. Okay. So this is a random variable, but it's not of size 2 to the n. It's of size n, which is of course much smaller. But they contain all the information that you need to reproduce in probabilistic way. Now, the fluctuations of this matrix G, they are measured by the cumulants. As I said, the cumulants serve to evaluate fluctuations of random variables. So here we have the family of random variables, actually random matrix. And the fluctuations, so in order to evaluate the fluctuations, we just compute the cumulants. So we try to compute the cumulants. So you choose a P spots on your matrix, P entries, I1, J1, I2, G2, etc. IP, GP, and you evaluate the P's cumulant on this. Okay, so these quantities are the ones that we would like to evaluate asymptotically. Well, when n goes to infinity, the leading cumulants, we know they scale approximately, they scale like n to the minus p plus 1. Okay? So in other words, if I look at this quantity, it's a big O of n minus p plus 1. Okay? But among all these quantities, many of them are just negligible. There are only a few of them are really of this order, n to the minus p plus 1. Okay? What one can prove is that this quantity will have a non-trivial limit. I mean, have a non-trivial limit. Yes, if the J1, Jp form a cyclic permutation of I1, Ip. Okay, in all the other cases, the scale is an order of magnitude smaller than this one. Okay, and well, if you assume that, for example, I1, we take points I1, Ip. So they correspond to sites on the interval, sites of our exclusion process. So we make a circular permutation with this I1 IP, which is so this corresponds to J1 JP being cyclic permutation. So in this case, this means that we are computing the cumulant of Ji1 IP, Jip, IP minus 1, and so on, until I2, I1. Okay, and this is of the order 1 over n to the p minus 1 times some function which depends on the situation of the I1, I2. So I assume that I1, I2, In, etc. They converge to some spots on the interval between 0 and 1. So I have some function GP of U1, U2, UP. Okay, and so we have this asymptotic expansion, and all the other cumulants are negligible with respect to these cumulants. And now it turns out that the GP are piecewise polynomial functions. And they are polynomial in each sector, which corresponds to a way of ordering the UI. So remember, the UI are numbers which between 0 and 1. So I call them U1, U2, U, etc. But of course, they are ordered because they are between 0 and 1. And the order, there's no reason to take them increasing, for example. So, and if we look at, if we divide 0, 1 to the p into sectors corresponding to the possible orderings of U1, UP, on each sector, GP will be a polynomial function. Okay. So this leads us to loop polynomials, which are defined by Denis Bernard and Tony Jean in 2021. So these polynomials are indexed by circular permutations of 1p, and they are defined as the value of the function GP on each of the sectors corresponding to a certain ordering. Actually, it depends only on the cyclic ordering. It is invariant by cyclic permutation. So, but it's not invariant by transposition, of course. So we take the limits of these quantities when, again, I1, I2, etc., In converge when rescaled to some spots, U1, U2, X1 here, X2, XP, and we get these polynomials, Q sigma. Okay. So these are called the loop polynomials. Okay, and they give the values of the function GP in each sector. So here are a few examples, just to show you how. So each Q, for each n, I index the Q by all possible circular permutations of one n. Okay, so each permutation, a circular permutation, I represent by putting one and then a permutation of the other elements. Okay, and so here are the values of Q. So of course, Q1, 2, there is only one permutation of two elements. For 3, you have two circular permutations, but the value of Q is the same. For 4, you have 4 values of the 6 values of the possible circular permutations, but the polynomial takes only 2 values. Okay, so these are very nice polynomials. They have you see that they vanish always at x1 at the first element. They always vanish when the last element is equal to 1. Okay. And in between, they have integer values. The coefficients have integer values, and the sign also are easy to predict from these formulas. Okay, so this was a formula that Denis sent me a few years ago and asked me if I could. He had a recursive formula for computing these polynomials. That's why he could produce the formulas. Yes?
I'm a bit surprised that nothing special happens when two values get close to each other, like x1 and x2, for instance, if they're equal. It's not a...
Well, you can check that this is continuous.
Okay.
That's what happens. Okay. This is obvious. Okay, the only thing you have to check is when you exchange 2 and 3, you get the same... when x2 is equal to x3, you get you look at the last 2 lines. When x2 is equal to x3, you get 5 times x2 and above and 5 times x2 below. So that's what happens. Okay. And now it turns out that the loop polynomials are actually free cumulants. That is something which is quite surprising. So in order to describe this, let me consider the set 0, 1, the interval 0, 1 with the Lebesgue measure. And let me define the random variables pi x by a function which is 1 on the interval 0x and 0 outside the interval 0x. They form a commutative family of random variables, and the product is of 2 of these random variables is another of these ones. It's just indicative functions of intervals. Okay. And the theorem is that, well, Q sigma of x1, x2, xn is the nth free cumulant of pi evaluated on x1, x sigma of 1, x sigma square of 1, etc. So that's a very surprising formula, because we have free cumulants, and as I said, free cumulants are really designed to deal with non-commutative algebras, and actually highly non-commutative algebras like free products. But here we have free cumulants evaluated on a commutative family of random variables, which is something which is quite unexpected, and it's a bit, it's very surprising. Actually, I found this formula, but before that I had a purely combinatorial formula for Q sigma, expression in terms of some trees, some Schroeder trees. And it took me some time to realize that these actually were free cumulants, and I've been working with free cumulants for the last 30 years, but still it took me some time to recognize that the Q sigma are really free cumulants, and I was very surprised to realize that. Okay. Okay, now as I said, the identification of the large now I come back to the problem of the density large deviation for the density profile of the SEP, the classical SEP. We know there is a relation between the SEP and the QSEP. So the SEP is a classical exclusion process. The QSEP is the quantum one. We have this relation, okay? And we can use what we know about the correlation functions, the cumulants of the GIJ. We can evaluate the thing which is on the right side using the cumulants of the using the cumulants of the GIJ. Okay, so using this relation, we'll be able to rederive the formula of Derrida and collaborators. So for this, I will define the scale cumulants of the SEP as this function, g of x1, xn. So here I'm looking at the classical cumulants, so the big K, evaluated on the occupation numbers, tau I1, tau I2, tau In. Okay, and I assume that the location of I1, In converge to some position on the interval 0, 1. Okay. If we look at x1, x2, xk, all different, then we have a combinatorial formula which expresses this in terms of so on the left we have the cumulants which are above. Okay, of course these cumulants they are symmetric in the x side because they are just cumulants of a family of random variables, commutative random variables, the tau I. On the right we have the Gn which are not are not symmetric. As I showed you, the Gn they take different values on different sectors in the interval. So, but there is one way of going from the cumulant, the quantum cumulants to the free cumulants to the classical cumulants, or let's say from the cumulants for the non-commutative random variables to the classical, which is take a sum to symmetrize everything by taking a sum of permutations, modulo cyclic permutations. Okay, so the quantity on the right is invariant on the cyclic permutations, but not invariant on the all permutations. Okay, so now this relation follows from Wick's theorem essentially, and now we have a link between the QSSEP cumulants and free probability, and in this way we can give a new construction of the classical SEP large deviation function. Now let me make a small digression. We'll just talk about so, as you know, the occupation number are Bernoulli random variables, so they only take values between 0 and 1. So if you want to know the joint distribution of n random variables which are Bernoulli, then this depends only on 2 to the n numbers. Actually 2 to the n minus 1 because the sum is 1, but okay. Essentially 2 to the n numbers. So we can reduce all the information, because we have Bernoulli variables, we can reduce all the information to the values of this non-coincident cumulant. That is the cumulants of size k, where bi1, bi2, bik are, so the bi here are just arbitrary Bernoulli variables, and we want the i1, i2, ik to be all distinct. Okay? So these numbers completely determine the distribution, the joint distribution of the Bernoulli random variables. And so now what I do is I will give a general formula for the cumulants. So this has nothing to do with freeness, random matrices, freeness. It is just a very general statement about Bernoulli random variables, about cumulants of Bernoulli random variables. We know that cumulants of Bernoulli, arbitrary cumulants of Bernoulli random variable should be expressible in terms of on these numbers. Okay, so 2 to the n numbers, and nothing more information. So we know there should exist a formula. The problem is to find one, so here is one. I don't know whether this formula is well known or not, but we derived it for the paper. If I look at the generating series of the cumulants of the Bernoulli random variables, well, this can be expressed. Also, there is a sum, a bit complicated sum. It's a sum of, okay, there is a combinatorial sum over, well, it's over connected bipartite graphs, and L runs over all labelings of the white vertices of the bipartite graph, and by distinct indices, and there is a weight to put on each graph. Okay. So there is some graph which is induced by this bipartite graph on the black vertices. And mu is some combinatorial factor, which is a factor Möbius function associated to a poset induced by the graph. And there is we have to divide by an automorphism factor of the unlabeled graph. Okay. So maybe just, I don't want to go into detail, I just show you one example. Here is a bipartite graph, one of the graph H that occurs here. So here, so I have a bipartite graph. If I look at the graph H, which contains only the black vertices, it is a complete graph. And it has, okay, so two, I say that two black elements are connected if they are connected, if they share a white vertex in common. Okay, so this defines the graph H black here. So in this case, you can compute the Möbius function. It is equal to 2. There are no non-trivial automorphism. And what you do is you label all the black vertices by some cumulants. Cumulants corresponding to the different labeling of the edges. Each edge is labeled by its the label of its white vertex. So it's a combinatorial formula that you can derive, and it's very general. The only hypothesis that you have is that you have Bernoulli-random variables which take only 2 values. Okay, so each time you have that, you can use this formula. I don't know. Maybe it's not useful, but at least if you're interested in binary random variables, but at least you have a formula. Okay, but in our case, it turns out that we are able to. Okay, so a word about how you get this formula. So it's you can be obtained using a theorem by Leonov and Chiryaev, old formula from the 60s, which use the theory of cumulants with products as entries. And you need also some graph theory which involve chromatic polynomials, but I don't want to enter into that. So it's a combinatorics. Okay. Now the formula that I showed you, sum of all graphs, it simplifies in the following situation. It simplifies in the cumulants scale like that, like the nth cumulant scale when big N, the number of variables goes to infinity, it scale like 1 over n to the 1 minus small n. Okay? And I assume that these converge to some function, say on 0, 1, or on, there is no reason to index I1, In, the B by the interval 0, 1, but I mean, if you want some other topological space, it doesn't matter. It's important fact is that you have a limiting structure for the cumulants. They converge to some function psi, which on some, say, topological space. But the important fact is that you need to have this scale, 1 over n to the 1 minus n. So in this case, the formula that I showed you, the terrible formula, only the contributions of graphs which are trees survive. So in the end, in the limit, you get a sum of the trees. And trees are much easier to understand than arbitrary graphs. Okay, when you have trees, essentially you have a composition of functions when you sum over trees, and for this reason we are able to do the asymptotic analysis. So for this, we introduce a generating function of the psi n. Okay, so the psi n is sorry. So psi is here. Okay. So it's psi n, there is a small n, which is missing. So we introduce a generating series of the psi n by introducing a function q and integrating a q of S1, S2, Sn with respect to psi n on our space. So we imagine that our parameter space rescale converges to some topological space. It may be a line, it may be a square or a cube or whatever you want, a sphere if you want. Doesn't matter. The important is that the correlation, the cumulants converge to some function psi, and you know how to evaluate psi. Okay. Now, in the scaling limit, then the free energy is obtained by solving the following variational problem. So this follows from the formulas I showed you, and the fact that you are making the sum only of the trees. Okay. For this reason, we can prove that the free energy has a limit, which is obtained by a variational problem, maximizing a certain integral. Okay. Sorry. Oops. Yes, okay. Maybe I should say that e to the s is... yes, okay. There is a formula for e to the s. If you remember, there was... W was just the Laplace transform of the... what is it? So W is the Laplace transform of the joint Laplace transform of the Bernoulli variables. So there is a function h, hi. Okay, so and e is e to the h minus 1. So that's the connection between this formula and the formulas that I've shown. I should have included the definition of... So you look at this formula, so you have this f0, which is on the right. You have there is some Legendre transform because you're maximizing because with respect to q to the s g over s, and you have this log of 1 plus e to the s g of s. Okay, so you are maximizing above g and q, and e is input, that is e to the h minus 1. Okay, so it's a functional of h. Okay, and well, actually, so I have just 2 minutes left. So it's okay because I have only two slides. Now we can apply this analysis to the preceding, to the case of the SEP and QSEP relation, in which we had, remember, we had this relation between we had the classical the relation between the classical and the free cumulants, and it turns out it is, well, I mean, this is a bit. I don't want to go into this, but there is something which is called the R transform in free probability, which was naturally here, which is, if you remember my formula, I had a formula between the generating function of the moments of a measure and the generating function of the free cumulants of the measure. And this is sometimes somehow hidden in the formulas that I'm writing here. But I will not give details, okay. And finally, what you get is essentially this formula for the large deviation functional for the SEP, okay, which essentially is equivalent to the formula of Derrida, Lebowitz, and Spear. Okay, so this formula comes from the general Bernoulli case, in the special case where my cumulants are given by a very special cumulant that I showed. Okay, I think it's time to thank you for your attention.
So, are there questions?
Yeah.
So the large deviation principle
looks
in quantum case similar to the classical one.
Okay, so I was not looking at the large deviation in the quantum case here. What I did is I looked at the Laplace transform, and I said this Laplace transform can be computed in a quantum way. Okay, but I was not trying to establish a large deviation, quantum large deviation principle. I was just using my knowledge of the asymptotic of the Laplace transform, which I got from the quantum case, in which free cumulants appear from some mysterious reason.
You believe in quantum large deviation principle.
Perhaps, but I mean, as long as you can compute cumulants, probably you can state something about the quantum version of large deviation principle. But we have not tried to figure out that. Okay. Oui?
One question. So, in the original formula you showed of the large deviation by Derrida, Lebowitz, and Spear, there is this function f you have to optimize.
Yes.
And in the new version, you had the g and the q.
Yes.
And I was wondering first how they are related, and also whether there is some understanding of this F, maybe in terms of the quantum model. I mean, a bit more direct, because in the classical case, the F comes there, but it's very hard to...
Yes, no, I mean, it's almost the same formula, except that when you do the optimization of a Q, I think you will produce the derivative of G or something like, or of log of G or something like that. Okay. You have to, I mean, you have to understand what is F0. So it's a bit complicated, you know, you have this logarithmic integral, so it's I mean, it's just a real analysis, and I should make it clear that this is at the physicist level of rigor. I mean, we have no pretension of providing a true large deviation principle, just, I mean, making computations and assuming that everything goes, limits exist, and if the limits exist, they should be equal to that. But I mean, it would be probably very hard to really make a mathematical proof of all this. I mean, the combinatorics is okay, it's just combinatorics, but analysis, of course, is much more difficult. Okay, so you have to understand this kind of equations that essentially involve inverting some power series, like we had in the relation between the moment series and the cumulant series. So that's some inversion series, and this will produce the last term in the formula. But this is not, we don't get directly the formula. We get the formula of Derrida, etc. by after some work. I mean, it doesn't come up naturally. But here the function G is well, the function G, the appearance of the function G, which is in this formula there is a function G, which is essentially the function F that we had before, and you see it comes. It is essentially the Legendre transform of F0 here. That's or it is related to the Legendre transform.
But it's not like a natural variable once you are at the level of the quantum model. It's something which comes with the cumulative.
No, it's really it's not at the level of the quantum, because we went from the quantum to the classical by taking a sum of all cyclic all permutations. We have symmetrized everything. So we are not really still in the quantum case. We have come down to the classical case, and but I would say that the function G is naturally coming from here, because it comes from this kind of graphs. But when you consider only trees, okay, when you sum over trees, actually what you do is you are composing functions. Like when Galson-Watson process, or you know. So this is hidden in this in the fact that here we are summing just we are just taking only trees in the limit, of course. In the exact formula you need all graphs, but in the limit only tree survives.
To what extent dimension 1 is important for your combinatorics?
Oh, it's very important. I mean, I don't see how you could. I'm not a specialist of the exclusion process. My thesis colleague, I know more about freeness, but it seems to me that in 2 dimensions it's quite intractable. I mean, I don't know what you think.
There's no exact formula in 2 dimensions, so that was the next question. I was wondering whether some simplification. I
mean, I don't think it's easier to do the quantum case in 2 dimensions than it is for the classical case. I mean, since you project on, it projects onto the classical case, so it could not be simpler. I mean, probably not. So here we have another way of arriving at the large deviation, but in the meantime we have found some fluctuation of a certain random matrix, which is really quantum. The correlation matrix is really a quantum object.
So if there are no more questions, let's thank Philippe Biane.
Thank you.